We'll be looking at how to calculate the design forces for chords. This applies to flexible diaphragms. The concept of chords is applicable to both flexible and rigid diaphragms, but the way we break down the statics assumes simply supported beams between lines of support, which is appropriate for flexible diaphragms. Let's jump right into it. First, we'll look at chord forces in a rectangular section of a flexible diaphragm. Shown here is, in green, a rectangular section of a diaphragm. Many diaphragm sections are rectangular, so we'll solve this in closed form. We have the diaphragm design force already smeared out into a distributed load W. That can be calculated as the design force, which I'm calling here V, divided by the length of this member. The length isn't dimensioned out, but it's understood to be the horizontal length. The reactions at either end, because it's assumed to be simply supported, are simply half of the load, which can be written as WL over 2, or the total load V over 2. From this, we can compute shear diagrams, straightforward, well known for a simply supported beam, and we can calculate a moment diagram. Again, this is straightforward and well known for a simply supported beam. The peak moment is WL squared over 8. Let's make a cut right at the center of this diaphragm where we have the maximum moment. This is what it looks like. We have at that center section a tension compression couple, and moment resistance is provided by this tension compression couple. Each of these forces, the tension and the compression, is called a chord force. We'll reinforce these sections of diaphragm in special ways so that we attract these loads in such a way that we can develop these tension and compression couples. Let's calculate the value of them. Set the moment, the peak moment, WL squared over 8, equal to the value of this couple. C is equal to T, so I'll just call it C times the diaphragm depth D. That's the resisting moment in the cross section. We can then solve for the value of chord force, and we have a closed form equation, WL squared over 8D or VL over 8D, depending on whether we have the value ready at hand for distributed load or for the total force in that section of diaphragm. Let's move on to our example. This is the example that we developed previously for shear forces in the diaphragm. We'll continue with the same example. I've also shown here the previous equation that we just determined, and let's calculate the chord forces for the two rectangular segments. Those would be the segments between lines B and C and between lines C and D. We'll work in tabular form. In this table, I'm showing in the first column the name of the segment, in the second column the value of the shear force in that segment. We previously determined this in another video. In the third column is the length of that segment, 30 feet for CD, 15 feet for BC. In the fourth column, I'm showing the depth of that segment of diaphragm, 30 feet for CD, 20 feet for BC. As an intermediate step in the next column, I'm calculating the moment. And lastly, in the last column, we're using the equation that's shown above to calculate the chord force based on the value of shear in that section, the length of that section, and the depth of that section. Let's locate the information that we found. For segment CD, we have calculated the chord forces right at the center of that segment. That's where the moment is the greatest, and that's where we calculated the value of the chord force. Similarly, for section BC, we found the value of the chord force right at the center of that segment. We'll see later what we do with this information. Let's move on now to the more complicated segment, the segment between A and B, which is not rectangular because of that little opening in the lower right-hand corner. So this is a sketch of that segment of diaphragm. It's not to scale, showing the values of distributed load on each of the sections, the reactions on each of the ends, and these values we previously determined when we did the shear calculations for the diaphragm. We also previously determined this shear diagram when we did the same calculations. We can also calculate the moment diagram, and it'll look something like this. I've indicated already one of the values, and that value is obtained by working from the left-hand side. We can take the area of the trapezoid on the left-hand side, and that's equal to the value of the moment that's indicated there. The average of 22 and 10 is 16 times the length of 10 feet, 160. To get the peak moment, it's a little bit more complicated. It's still basic statics, but we'll remind ourselves of what the calculation looks like. First thing we need to do is find the distance to the point of zero shear. I'm calling that distance x. That distance can be found by saying that the change in shear, which is 26 kips, is equal to the area underneath the load diagram. The area underneath the load diagram is the value of the load, 1.8 kips per foot, times the unknown distance x. Rearrange the equation, solve for x. Once we have x, we can calculate the maximum moment by the area of the triangle. 1/2 times the height, 26 kips, times the base x, gives us the value that's shown at the peak of that moment diagram. Now let's get rid of all the stuff we don't need. We'll keep the moment diagram, and we can use those moments to calculate the chord forces at various locations along segment AB. The first location is going to be at the edge of the opening. That's the largest value of moment for the smaller 20-foot depth of diaphragm. So the chord force then is going to be the value of moment, 160 kip feet, divided by the depth, the 20 feet, and that gives us a chord force of 8 kips. The 8 kips occur at the location that's indicated on the diagram. Next, we'll calculate the chord force at the point of maximum moment. We take the value of moment divided now by the 30-foot diaphragm depth, and we get a chord force of 6.26 kips. That chord force occurs at the location shown. So let's move on and summarize all the information we have so far and see where we would go with this next. This diagram shows all the values that we've found for the chord force and the corresponding location. Let's think about what this means for design. So here I'm showing the diaphragm again. I'm showing the location of the chords. Now at this stage, if you're new to chords, it can still seem a little bit abstract. But what these are, they're simply continuous pieces of the diaphragm that are specially reinforced. Some examples are with steel straps in wood buildings or additional rebar in concrete buildings. We're not going to design these members for a different force at every location. We'll choose a few critical values of the force, and we'll use that value of the force to design the whole chord. For the chord that's on the left side, as well as the chord that's a little bit internal, adjacent to the opening, we can identify that the largest value along those two chords is 8 kips. So we'll simply design that entire member, that entire reinforced area, to a force of 8 kips. Along the other two, the force is a little bit lower. I'll probably want to keep them the same. I probably don't want to design each of them differently. I might say that I'll design both of those for the larger value of 6.75. Or maybe even that's too detailed. Maybe it just makes more sense to design all of the chords on this story for the 8 kip force. One note to keep in mind, of course, this is only one direction of behavior. This is for loading parallel to the grid lines A, B, C, and D. We would need to repeat this process for loading in the vertical direction perpendicular to grid lines A, B, C, and D. One additional note is that I'm showing only the main chord design forces. There's a lot of detailing that we need to take into consideration that I haven't done yet that we'll cover later. So this is, in a sense, only the beginning of the story. We're getting close to finishing this example. In the next video, we'll look at what we call collector forces. And once we've done that, we'll have completed the example of determining the design loads for all the different aspects of diaphragm design: shear, chord forces, and collectors. See you next time.